Well, here we are again. Dr. Bettina Heinz is here to teach you some more chemistry. Today we have scheduled measurement 2 and of a 2-part series on measurement. These are the topics we will discuss today. Dimensional analysis, we already started that in the last episode, the factor label method. We will continue with this today quickly. Then we will go into some unit conversions, exact numbers, we already learned about that, mass, weight, and volume, temperature, and their actual measurements, and the devices we use to measure these quantities. Then we will learn about density and specific gravity, which is very much related to density, the Archimedes principle, or the water displacement method to measure the volume of irregular objects that we need to calculate density values. And then we will also give you a little exhibition of the various tools that we use for measurements, those that I could bring here into the studio. Let's first continue where we were with the dimensional analysis before we go to density as a definition, because with the help of density I can explain to you many of these concepts. Remember we talked about significant figures and calculation with significant figures, and here you will see again what we had on the screen last time. The given that we want to calculate with should go before, up front, and then we have the conversion boxes as we need them, and we will, in this type of unit conversion calculation, we will always set it up that the unit that we want to get rid of has to be in the denominator of the ratio fraction, and the new unit that we want to come up with in the end on the right side of the equation has to be in the numerator portion of that ratio. This is called dimensional analysis because we analyze the units and set up the ratio. Remember, we can set it up one way or the other, upside down or whatnot. So here it's inches over feet, but we can also say if we want to convert inches into feet, we would have to switch that ratio and have the feet on top and the inches on the bottom. So we always have to make sure we can cross-cancel the old unit and come up with a new unit. So this is what we're always doing in science and chemistry, particularly. Here's another example. 2.8 feet are how many yards? So here we have what we are given. The dimension, remember, is the number as well as the unit together. So what we want to change comes up in the front. Then we insert the conversion ratio box, so to speak, and put it neatly in parentheses so we can keep it nice and boxed in. You don't have to, but I think it's very appropriate to do because it helps you to be cleaner in your calculation. So here we see we set up the ratio 1 yard is 3 feet, everybody knows it, and 3 is just a fixed number. It has to do part of that conversion ratio, so it's not a measurement. So only measurements we have to consider as significant number of figures. So here we have 1 over 3. Feet cancels, so we cross cancel and we come up with yards. You see the yards have to show up after we do all that calculation. Now when we divided 2.8 by 3, they get 0.933 period. So many 3's behind it. Remember, you will notice that we have too many sig figs here, too many significant figures. We have to tailor it down because our old measurement had only 2. So we have to tailor the result down to 2 sig figs, and therefore I have to drop one of the 3's. So you see, now we have 2 significant figures. The 0 is just a decimal holder. So exact numbers never change. So they are given ratios. Like 1 foot will always be 12 inches, regardless of whether you put your own foot in there or not. This is a standard of measurement. 1 yard will always be 3 feet. So that's a fixed number, exact number. Now let's do a little bit, a little tougher conversion problem with the dimensional analysis. If we have 2.8 square meters, how much is that in square nanometers? So a nano means 10 to the negative 9 meters. Okay, so we have what we have given here on the left. The conversion ratio is, we know that a meter is 10 to the 9 nanometers, or we could say 1 nanometer is 10 to the negative 9 meters. We could do that too. It's the same type of ratio. However, we're dealing with the squaring of that ratio. We have to keep that in mind. And when we square it, we have to square everything inside of this bracket. So that means 2.8, 10 to the 9th will be squared. The nanometers will be squared, and the meters will be squared. Everything has to be squared. So we have 2.8, 10 to the 9th squared, which is then practically multiplied. So 2.8 times 10 to the 18th power will then give us a completely different number if than when we wouldn't have considered that coefficient squared. So you see it's actually 2.8 times 10 to the 18th power of nanometer square, because the meter squared, once we squared everything inside the bracket, will cancel out, and the old unit is then gone, and the new unit is then here on the right side. So this, you see, is very important, the dimensional analysis. Sometimes we need more unit conversions, so we can add more brackets of ratios behind the first one. So you see later on we will learn about using more conversions in one calculation. So you can make a tapeworm of conversion ratios and still come up with a unit that you want to have in the end. Now let's define what density is. Density is a very important property, physical property of matter. It means the compactness of matter. How much matter do I have in a certain given area or space? Rather space, volume we should say. So it's actually mass over volume. How much mass is in a certain volume of substance? So some material is a little tighter packed, some material is a little looser packed. You know, the gases have a very low densities, the liquid have a sort of in-between density, and the solids usually have a high density with the exception of water, which is unusual. So density is defined as mass of substance, usually measured in grams, over the volume of the substance, usually measured in milliliters. So we can say D equals M divided by V, or M over V. Or we can say the mass is density times volume, or volume is mass over density. So we can do a variety of calculations. Let's say we have the mass given and the volume given, then we can calculate the density. We can have the density given and the volume given, then we can calculate the mass. We just have to rearrange this equation. Or if we have the mass and the density given, we can determine the volume. Just as an example, we have here some density of metals. We have the light metals, for instance. We have heavy metals like lead, mercury, and gold. And gold is really the real heavy metal that you wouldn't expect to be a heavy metal. It's 19.3 grams per milliliter. And mercury as a liquid metal is 13.6, pretty dense. Lead is somewhere in between. Silver is a little more on the light side. Aluminum is really a lightweight metal, light density metal. What about the density of liquids? Now water has is an unusual substance, and we thank water for it because life wouldn't exist here without water. Water has a very handy density value, and that's 1 gram per milliliter. So if I say measure 20 grams of water, then I can just pour out 20 milliliters and take for granted that the density is 1. So you can practically equate these two units. Now carbon tetrachloride is an interesting organic solvent that used to be used in the dry cleaning business but produces, unluckily, some cancer of the liver. So it's not used anymore, but it's still an excellent solvent. It has a density of 1.595 grams per milliliter. So it's a heavy liquid, we could say. If we mix those two liquids, which are non-miscible, by the way, they don't mix, it's just like oil and water, then you can see here at the little test tube illustration here that the lighter liquid will be up top and the more dense liquid will settle at the bottom. So it's also dependent on gravitational forces, of course. Here we have some questions you can sort of ponder. Water has a density of 1 gram per milliliter. How much volume does 1 gram occupy? Well, 1 milliliter, of course. A 1 liter sample of carbon tetrachloride weighs 1.6 kilogram. What is its density? Oh, I can tell you right away. It's 1.6 kilograms per liter. But then remember, if we want to get those units in grams per milliliter, we have to do a little conversion. Or the density of mercury, 13.6 grams per milliliter, is given. What is the mass of 50 milliliters? Well, you just plug in the density, and there you have the volume. So we use this formula and calculate it. So you see that's very flexible what we can do here with density. Now, a regular object can be calculated. But what about an irregular object? So here's a lady who is just married and she has a gold wedding band, and she wants to check to see if it's really gold and not some cheap material that you can buy in a 5-cent store or something. So how can you determine that? You just figure out the density or measure the density. So you need to weigh the ring, and then you have to do the volume calculation. But it's very difficult mathematically, although it can be done. It's much easier to use the liquid displacement method or the water displacement method. And Archimedes, a Greek of ancient times, observed this phenomenon, and that's why we honor him by saying this is the Archimedes principle. So an irregular object can be easily determined for its volume by just submerging it into a given amount of liquid where you know the volume. The initial volume is known, so we can use a measuring cylinder to determine that, and then we just plunge in the ring, and then automatically the water level will rise at the exact and will be for the exact amount of volume that the solid object occupies in itself. So this is what we call water displacement. Now you all know when you take a bath, you don't want to fill it up too high, because when you get in there, the level will rise, right? So you are displacing a lot of liquid. If you want to find out your own volume, well, that's not so easy. You have to be completely submerged, and somebody has to measure the rise of the liquid level. But it's not quantized, the bathtub, so you can't really tell. So here we have a graduated cylinder. We have to be careful that we read the right volume difference. Delta V is the final volume minus the initial. And that is the same as the actual volume of the ring then. And then when you mass the ring or weigh it, you use some scales. Depending on what type of precision you want, you can use the beam scale, which all the institutions have in abundance now because they're arranged out. New digital top loaders are bought by the funds, so you can use a top loading scale. Or if you really want to be extremely precise, you use what we call an analytical balance. Okay, so we weigh the ring, and when we have the mass of the ring and the volume that it has displaced in the measuring cylinder, then we divide these two values into each other, and then we get the density, and then we can look it up to see if the density is high enough to qualify the ring as of being mainly of gold. Now pure gold ring is practically impossible because it's too soft, the metal. We talked already about some measuring devices, the measuring cylinder, the scales, and I will show you some real-life equipment here soon. But before we go on in showing you the equipment, let's look at some other devices that are used, or tools that are used for the measurement of volume, mass, we already have seen, and temperature, of course. So these are very important variables that we need for our scientific studies. Measurement devices for volume, well, depends again what type of precision we want. We have different sizes of measuring cylinders with different scaling, different intervals or increments. So we can read to the nearest tenths or the nearest hundredths. That's very important because it gives us more significant figures. And the more significance we have, the more accurate we will be in our calculations. But often we don't even want so much precision. If somebody says weigh out or measure 20 milliliters of acetone and use it as a solvent, then I don't have to be precise. I just need around about 20 milliliters. Now, what if I want to make a certain solution, dissolve something in a given amount of liquid to have a certain concentration? Then I usually use the volumetric flasks that measure one particular volume. They have a little ring around it, the neck of the flask, that indicates the volume that we can measure. So we can weigh out the crystals, dissolve it in some of the solvent, and then fill it up to the margin, shake the flask, and then we have a certain concentration. So they come in all sizes too, in super large and very tiny ones. When we want to dispense some liquids, we usually use pipettes. And there are also two types of pipettes, the volumetric pipettes, which only dispense a certain amount of volume. We have them in different sizes and different degrees of precision. And for titration purposes, when we want to do quantitative volumetric investigations, we use the burettes. There are two types, one with a valve or the stopcock right below the glass column, and one sort of leading outward a little bit, which is a little bit more elegant and easier to use. Here we have a little graduated pipette. So here we can measure different types of volumes that we want to dispense. And a syringe is practically like a pipette, only that we use a plunger and a sharp needle to dispense medications, right? We have different degrees of precision, different maximum volumes, etc. Different degrees of error, depending on what kind of increments we have, etc., etc. And if we have a regular object and we want to determine density, then we can actually also calculate the volume. Like this geometric object can easily be determined, the quarter, by the different side lengths. So A times B times C, length times height times width, and we get the cubic length units. A cylinder is a little bit more difficult. Here we have to remember that it's height times area of the circle, which is on top and at the bottom of our cylinder. So we need the radius and pi, which is 3.414. So pi times r squared is the area times the height, and we get the volume of a cylinder. So we don't have to throw it into the measuring cylinder, and often people break the cylinder then or the measuring cylinder by plunging something too violently into the liquid. Something very related to density is specific gravity. Many people get that mixed up, and we want to make sure that doesn't happen to you. Specific gravity, usually when we have specific something, it's usually a value based on a reference. So specific gravity is also considered as a ratio to a reference. And there's no real symbol for specific gravity. So I'll just say SPGR for short. So specific gravity is defined as the density of a substance in grams over milliliters, or whatever units you have, over the density of a reference substance. And it's usually water because it has such a handy number. It's just plain old 1. So that means the only difference between density and specific gravity is that density has units and specific gravity doesn't, because they cancel each other out. That's the only difference. Specific gravity is more used in industry and for commercial reasons, like in the study of gems, etc. Jewelers use specific gravity more. So the density of gold is 19.3 grams per milliliter. The specific gravity then, what is its specific gravity? Well, very easy. 19.3 grams per milliliter over 1 gram per milliliter gives us 19.3. So you see it has no units. Now here's some food for thought. Density is reversed for water. Normally the density of a solid phase of a certain substance is higher than the liquid phase of that particular substance. But for water it's reversed. So ice cubes float in water. Why? Because the density of ice, or the solid form of water, is less than its liquid form. That's why icebergs also swim in the ocean, and the Titanic had the fate that it had. If it would be another substance, the solids would sink to the bottom. But that doesn't happen. Here's a good question. How much of the iceberg is above water, how much below? Or how much of an ice cube is above the liquid surface and how much is below the liquid surface? It seems interesting, but it's practically the same ratio as the mass ratio of the elements in water. So 1 to 8, or 1/9 to 8/9. And people talk a lot about what if the icebergs start melting. Well, the icebergs, if they melt in the ocean, will that raise the level of water, or will it lower the level of water? Well, if you want to find out, you can do that at home. Just take a glass of water, put an ice cube in it, and wait till it melts and see if the level of water has risen, dropped, or stayed the same. So that's an interesting experiment that you can do at home. We talked a lot about significant figures. And here is a good example of how we work with significant figures. Here's a problem for you. A gas at 25 degrees exactly fills a container previously determined to have the volume of 1.05 times 10 to the 23rd cubic centimeters. The container plus gas are weighed and found to have a mass of 837.6 grams. The container, when emptied of all gas, has a residual or remaining mass of 836.2 grams. What is the density of the gas at 25 degrees? So you see that's a word problem. You just find the things that are important. You need the volume, that's a given. You need the mass. And remember, we have to subtract these two values before and after removal of gas. So the difference is important. So we have 837.6 minus 836.2. And notice we have 4 sig figs, but when we do the subtraction, it turns out to be only 2 significant figures. So the number of significant figures can change within a calculation. And that will be the new determining factor as to what type of significance you have for your answer. So now it has changed to 2 significant figures. The volume, however, was 3 significant figures. And when I divide these two values, then I come up with a result that cannot be more than 2 significant figures. So it's 0.0013 grams per cubic centimeters. So this is important to keep in mind when you do calculations. Last not least, we are going to do temperature. Temperature scales. We have different scales, as you know. We use Fahrenheit here. Celsius or centigrade is the SI system, or a derivative of the SI system, a metric system at least. But the actual SI unit is Kelvin. Here, the intervals are each 100 degrees, meaning the freezing and boiling of water. For Kelvin and Celsius, it's 100 degrees. But for Fahrenheit, it's 180 degrees. So it's much more degrees in between. And here the conversion formulas. Kelvin is centigrade plus 273, or centigrade is Kelvin minus 273. Celsius is 5/9 times Fahrenheit minus 32. Because notice that 0 degrees is where freezing of water is observed, the freezing point, and in Fahrenheit it's 32 degrees. So you see you have to add or subtract the 32 depending on what type of conversion you want to make. And what's very important is that the degree interval is different. And this will be shown in our next view graph. That's what often people don't understand, is that the increment, the degree increment, is certainly much different. Centigrade and Kelvin are exactly the same, but Fahrenheit is practically 1.8 times the length of an equivalent centigrade or Kelvin degree. So you see, actually we have to use that interval as shown here. Now, quickly, we want to show you some real equipment. Here's a measuring cylinder. Here is a volumetric flask. And here is a burette. And here is a scale, an old triple beam scale. And that is the end of our show today. See you next time, and I enjoy talking to you. Bye.